सामने आ जाइए।
Namaste, good morning to everyone. In a short while from now, we will start today's session, technical session, and technical talk by Peter Farmer from Sweden. Meanwhile, I would like to invite Dr. Aman Verma for interacting with all the participants, and you may discuss if you are facing any problem regarding this hands-on sessions. So over to you, Professor Verma.
Hello.
Yes, sir, you're audible.
Hello everyone, and that session is little bit delay because Professor Panda is being ready, and there it's a very early morning in Sweden. It's about 5:45. It's about 6 a.m. So he will be joining within 10 minutes. So that in general, such type of workshop or hands-on training we provide for 1 week, 5 to 6 days, and we have confined that hands-on training in 3 days, and we are trying to do our best, and Mr. Narendra is also working very hard. So I think that new learners, that material modeling is new for very new for them, and they are really facing some problems because that Linux operating system is very new, and if anyone just aware of Linux operating system, then that sister tool, this is also new, and such type of this molecular modeling tool that is really new, and maybe interacting, or sometimes they face that this learning is a little bit boring because everywhere just commands, and sometimes so many errors are there. So just keep patience, and I promise you will enjoy learning. Just this is the motto of mine. So is there any problem or difficulty you're facing? You can discuss here because we have 10-minute time to wait for Dr. Panda, and I think Tripathi sir is also here. Manan Tripathi, I have seen he has joined. Yes, so Narendra, are you here?
Yes, sir. Good morning,
so
sir.
I think I should give you 5 minutes to discuss the opportunities in the field of material modeling for MSc and new PhD joining students, as you are there after learning SISTA in India. So what will be the benefit if that MSc previous final students, physics, chemistry, maths students are learning this material modeling? So please give some brief of your journey, as well as what they can do, what are the opportunities they will have for PhD in other countries, just away from India, with a good scholarship. Yes, Bhanu is also here. So Bhanu can also share their experience of learning. So first, Narendra, you will be you will talk.
No. I prefer if Bhanu will.
Oh, Bhanu, yes, first. Bhanu, say something.
Yes, sir. I just joined. I didn't hear like what you were saying. No, sorry. Good morning, sir.
Good morning. So, share your experience, how you learn this tool, and you are enjoying or not, and your work.
Oh.
How is Divya?
Oh. Yes, sir. Like first time I got exposure to this stuff from my supervisor. Then I went to Sir Mohanlal, Professor Mohanlal Verma sir's lab. No. Like I spent there around 1 month, and I got the basic idea, and from that basic idea to this, whatever we can implement, no, in this GFT tool. I learned from your nano lab only, sir, from Chhattisgarh SSTC only. And there was, I think, Keshav sir, Narendra and Vishal was there, and Swati ma'am was also there. Like I got to learn like everything about Siesta from that lab only. Otherwise, I already knew about Siesta. Like, okay, it's a DFT tool, we can use it for simulation and all. But the basic knowledge, everything, I got to know from your company only, sir, from your guidance only. So it has been a privilege to know you and to learn from you,
Okay,
sir,
okay.
your group and and now that tool is very helpful, no, sir. Like if we don't have any idea about open source and all, it's very hard to carry out the research, no. Like we already know that there are many good softwares, but they need huge amount of money to buy those codes and all. And for to be an independent researcher, it's not possible, I think. So it's very helpful if we can at least learn few open source code, no. And when it comes to Siesta, it's very user friendly and all. Like we can simulate many things using Siesta, and it has been a very good experience to learn this code. And we have been trying to implement this one in our studies and all. So I think once we become an independent researcher, I think Siesta is the code that we are going to carry out our studies with.
Yeah. Okay, Harsa is also here. Harsa joined.
Who, sir?
Yes, Harsa. I think this Harsa is our Harsa or some new Harsa. Are you okay, Harsa? Do you know Harsa?
No, sir. I think
NIT?
no. One ma'am was there. Harsa ma'am. I think NIT.
Yeah,
She
yeah.
was from NIT. I think.
She's doing good work in that water splitting. So her work is that thermodynamical properties and water splitting. Her work is good.
So my area of research is currently hydrogen storage only. Like I haven't switched that topic. Like currently I'm working on hydrogen storage only.
Hydrogen
interaction
storage.
of hydrogen molecule on low dimensional material. And
so in hydrogen storage, is there a requirement of van der Waals interaction?
Yeah, we have to implement, sir. It's mostly surface interaction only, no? Like so if we don't implement that one, the energy that we get, the energy might be including some errors. So it's better to use van der Waals interaction. And I think in Siesta, it's van der Waals interaction is only DF, I think, and that is the energy is nearly equal to D3 correction. That dispersion give me D3 correction. So we can implement that one, I think, so D3. And whenever we do this one molecule adsorption study and all also, I think we have to implement that dispersion correction, DF.
Good.
Yeah.
And that response from Sajal is very good. Sajal is working day and night. I think his band plot and other plots. Good energetic Sajal Biswas. Yeah. Where is Sajal? Are you here?
Yes, sir. Yes, sir.
From where you are?
Sir, I am from West Bengal, Nadia district, sir.
Okay. So previously you have contacted me, no? I think your name is.
Yes, sir. Previously, I contacted you regarding some facts, and I frequently watch your YouTube channel, and most of the thing I have learned from you, and learning from you is a great opportunity for us. And and I am assistant professor in a college. There is no infrastructure, but using a simple PC and Linux operating system, I can do such kind of wonderful experiments, sir. Very nice experience, sir. Amazing, sir.
Okay, so in this workshop, you have something new, some new thing to learn, or you already?
Yes, sir. New thing, very much new thing. I am constantly learning from you, sir. And you well said that this kind of workshop is limited to 3 days is very very disappointing for the learners. And the supports we are receiving from your end all day and night is very well, and giving a ray of hope for us, sir. Thank you very much, sir.
Okay,
And
okay, yes.
I think in the near future, when I shall got stuck in any point, receive help from you. Thank you,
Yeah,
sir.
sure. I'm always ready. Yes, now our speaker, Dr. Pritam Panda, is with us.
Yeah.
And
Hello, Dr. Boma.
yes. Namaskar. How are you?
I'm good. Sorry for the late because it's
Okay,
6:30
very
in the
early
morning.
morning.
Very early morning. Yeah.
Okay.
So yeah, pleasure to meet you, and very nice to see that many people are enthusiastic to watch my presentation. Yeah, it's nice to be here.
Yeah.
Thank you very much.
I am also a learner. Many things I learned from you.
Thank you very much.
Okay, so
Hi, Vanu.
okay, I should
Pritam sir, how are you, sir?
I'm good. Thank you.
It has been privilege to see you here, sir. Like I
Yeah.
just joined you. I
Abs-
saw that one no schedule, sir, that you are going to present here also. So I just very happy to see
Absolutely.
you, sir.
It's very early
Looking
morning
forward
here.
to listen to you, sir.
Yeah, absolutely. Thank you very much.
now mic to Rasmi Priya. Please start the session.
Yes,
And,
sir.
okay.
Good morning, everyone. Now it's my great honor to introduce Mr. Pritam Kumar Panda, sir. He is assistant with doctoral in the Department of Physics and Astronomy, Uppsala University, Sweden, under the supervision of Professor Rajiv Ahuja and Professor Yogendra Kumar Mishra from Max Clausen Institute, Nano SYD, University of Southern Denmark. He has worked as a junior research fellow in Biology Lab, KIIT University, India. His expertise includes computational biology, biophysics, 2D material modeling of electron transport in nanoscale device, and computational modeling of nanoparticles. He has published more than 57 research papers. So I would like to invite Pritam Kumar Panda, sir, for his talk. Please welcome, sir.
Thank you very much for the introduction. It was a nice and pleasure to be here. I'm going to share my presentation draft. So. Can you see my screen?
Yes, Dr. Panda. We are able to.
Yeah.
Why?
Yeah, okay. So yeah, good morning, all of you. It's very early morning here. I think in India it's 11:15 over there. So good morning, everyone. I am Pritam. I'm a researcher in Uppsala University, and I am from the materials theory group here in Uppsala University, working under the supervision of Professor Rajiv and Professor Yogendra Mishra from Southern University of Denmark. So today's topic will be regarding the genome to genome. This is the term that I coined during my PhD. And I gave a catchy moniker to do some translational research interfacing molecules with nanomaterials. So this will be a general talk. I mean, I'm not going to deep dive into the results or something. I just give you an overview. What are my works that has been done over here, and why this term I have given like genome to genome, and how I have done some translational research on interfacing molecules with different nanomaterials. It ranges from zero-dimensional materials to three-dimensional materials as well. So, and the catchy moniker that you see, that genome to genome, it's a term, as I mentioned, that I coined by me, and by bridging the concept of biophysics and quantum physics, which abbreviates to genome, genetic organization of the multicellular organism and their enzymatic reaction, to quantum nanostructured materials for energy scavenging applications. And it's a combinatorial approach using computational methodology in biophysics and in material science, where I study the interface of the molecules interacting with interacting with different type of nanomaterials. So today's topic that I'm going to cover based on three main aspects. One is electronic transport at the nanoscale, where I do biosensing of DNA, amino acids, and different gas sensing. Number two is the contact electrification with these nanogenerators. And the third topic would be nanomaterials with the different complex, architectures like, as you see on the right-hand side, the zinc oxide tetrapods, So these are the three main areas where I am working on, and these are some of the topics that I'm going to, cover today. So different types of applications are there. You see the first topic, that is biosensing or electronic transport at the nanoscale. I think Dr. Burma is one of the most searched, tutorial. If you want to learn electronic transport, then you go to Dr. Burma's tutorial on YouTube, and then next comes to me, because I do also some tutorials inspired by Dr. Burma. So regarding the first application, that is solid state sequencing, as we say, this is applied for personalized medicine, environmental sensors, and different water purifiers as well. The materials that I have taken, 2D materials, they are also widely used for different water purification systems as well. And the second topic, that is contact electrification, the term that is coined by Professor Zhonglin Wang. And I have been fortunate enough to work with him. He's one of the great scientists and the scientist behind the term turboelectricity or contact electrification. This can be utilized for sensor for smart home lighting, smart wearable devices, drug delivery, and different power transformers. The third thing, which I work with Professor Yogendra from Southern University of Denmark, is based on nanomaterials with complex architecture that is based on 3D materials, which is called zinc oxide tetrapods. And that was a very good antiviral agent. And whatever the research that I'm doing, those are targeting to the sustainable, one of the key goals of sustainable aspects, that is life below water. So different types of computational methodology I use, because this is a combinatorial technology. So for the density functional theory, I use WESSM, and for electronic transport, that was inspired by Dr. Verma's YouTube, is TransIESTA. And I use some classical dynamics, because dealing with billions of atoms and millions of atoms is not possible in DFT. That's why I use classical dynamics such as molecular dynamics, ab initio molecular dynamics with WESSM, dealing with few atoms, to classical molecular dynamics using GROMACS and LAMPS. And they use different types of parameters in order to get some insights into their properties. Okay. So I'll talk about electronic transport at the nanoscale. This is quite a wide topic, and I think the workshop is based on electronic transport calculation using siesta, and in general the siesta use. So I have used DNA biosensing techniques, protein biosensing techniques, those are amino acids, and gas molecules. There are different toxic molecules in the environment. So those gas molecules has been sensed by using different types of 2D materials. So the materials that I have used is gallium sulfide, and carbon nitride is one of the analog of graphene, which can be used for water purification system. And bismuthine, particularly bismuthine, has been used for sensing the different gas molecules. As you can see on the right-hand side, this is the nanomolecular electronic setup. And this has been done by using gold nanoparticles, and then bridged with the different types of molecular junctions like PPDT and TPDT. And it can be used for sensing different types of gas molecules. Okay. So the motivation came when I published a paper in Nature Medicine. I was working with the University of Freiburg, Germany. And what we have done is mostly next generation sequencing. the technology, the transport technology that you see over here, and whatever the DFT technologies that has been used, they are widely used in different universities, different companies, and they are used to treat different types of cancer patients. So in here, what you see in the Nature Medicine article is we have extensively used these machines, these Illumina machines. And I was baffled by the technology that has been used widely for next generation sequencing. And you can see that the technology that has been used in Illumina or any of the sequencing device is semiconductor-based technology. So that's why it allows me to work on different types of 2D materials, which has semiconducting behavior, and that allows me to do some transport calculation by using density functional theory. So in the right hand side, what you see is the typical setup of electrodes, 2 electrodes that we take of the same material or maybe from different material, and the scattering region where different molecules are being sensed. So this is a typical example of gallium sulfide monolayer with the DNA basis, which is adenine and thymine, guanine and cytosine. As you can see here, it has quite high range of sensing towards guanine and cytosine rather than adenine and thymine. I mean, this is the case for all the materials. I think whenever you do electron transport calculations with 2D materials, the sensing would be more towards guanine-based space and cytosine-based space rather than ANT. This is a typical result that you get. The next application is one of the peculiar application of different 2D materials. I have seen in 2020, University of Cambridge University, first time they proposed the amino acids that can be sensed in different 2D materials. So I have taken an analog of graphene, which is carbon nitride, GC3N4 monolayer. The typical setup is almost similar. And I have sensed different types of amino acids. So there are 20 different types of amino acids and 2 different types of another amino acid. So in total, there are 22 different types of amino acids, including pyrrolysine and selenocysteine. So what we have observed over here, I mean, this technology has been used in water purifiers. So like different water purifiers you have. So those purifiers, they use carbon nitride, the analog of graphene, that can sense the bacterial organisms or the bacterial proteins, and they can be used to filter them out. And by interacting with the analog of graphene, I mean, this graphene nitride has a good potential of an antibacterial agent. So the combination of density functional theory from here and a combination of molecular docking and molecular dynamics, where you molecular dock these 2D materials with different types of bacterial proteins, and that can affect the system, or that can kill the bacteria. So this is the technology. You can read my paper. I can send you the list of the papers which has been published based on the results that I'm showing. The next thing, this is a quite interesting setup. Here in Uppsala University, they have done some experimental analysis on that. And as you can see, they have mentioned me that, can you do some DFT calculations based on the experiment as a gas sensor? I said, yes, why not? Then I followed the tutorial from Dr. Verma and tried to establish the same. This is a nano MOAD, nanomolecular electrode junction, where I used gold nanoparticles to construct the device with different types of gas molecules, sensed on the top by using a molecular junction called BPDT or TPDT. Okay, and this device can sense based on 2 different factors. One is chemisorption, another one is physisorption method. And this is a very good technology to sense the gas molecules. So this particular device is inclined towards NO2 sensor, nitrogen dioxide sensor, rather than NS3 sensor. Okay, I'm just going to show you one video by using Molden. That's one of the software for visualization, and from the transport calculation, how you can do some visualization on the basis of physisorption and chemisorption. So yeah, these are some of the results that you get from electronic transport. So one is current and voltage graph based on the different voltage parameters, and the transmission graphs where you see at the Fermi level the rise of the peak, where different types of gas molecules can be sensed at the Fermi level. Okay, the high number of transmission peaks at the Fermi level, that means it has some types of resistance in the device. So this is one of the video that you can use by using Molden, and I think Dr. Verma is going to teach you about how the mechanism works and how you can utilize DFT analysis to visualize this kind of platform. So watch this video a little bit. You see the molecules and the junctions where the gas molecules have been adsorbed. One is chemisorbed and one is physisorbed. So you can see the conformation of the structure has been changed when it's chemisorbed, and during the physisorption, it's kind of stable. And this is based on the adsorption of chemisorption and physisorption. As you can see, in case of TPTT, triphenyl diethyl and biphenyl diethyl, the triphenyl diethyl has a chemisorption on. Seen in the previous video, the conformation of the structure has been changed. Quite a lot, positive in binding energy, which is not good. Generally, what you get the binding energy is in negative areas, but this has a particular system for sensing nitrogen dioxide molecules. It kind of adsorbed on the surface of these type of molecules. And yeah, one of the application of solid state nanopore sequencing, nanopore sequencing is quite famous, and that has been devised by one Indian scientist here in Oxford. And you can see that these nanopores can be used also for sensing different types of DNA, amino acids, and even different gas molecules. But mostly it has been used for sensing DNA molecules. So this nanopore sequencing is also similar to whatever the technologies that has been widely used by Illumina. Okay, so what I've done is I've taken 2D materials, and this is the particular snapshot of a paper from Glavin et al. You can read this paper. This is a very nice paper describing how the P-block elements can be used to devise nanopores to sense different types of DNA molecules. So I have taken a series of the 2D materials and try to devise a nanopore-based technology. You can find all the tutorials based on nanopore sequencing as well. It's there in my YouTube channel. So you can devise such kind of electrode setup or the scattering region setup, the transport setup, and then you can sense different types of DNA molecules. So in all the cases, as you can see, as I mentioned previously, it has quite a good sense for the guanine molecules, because guanine and cytosine almost they have triple head bonds, and they are slightly inclined to be interacting with different types of 2D materials. So the results in the up is based on DNA sequencing. I have used antimony, arsenine, bismuthine, germanium, MOS2, phosphorin, silicine, stannine, and you can use all different types of 2D materials to sense DNA molecules. And in terms of amino acid sequencings, it has been categorized into different categories like non-polar, polar amino acids. So every amino acid which has a functional R group, they are based on different types of functional groups, they are sensed towards different types of 2D materials. In terms of gas sensing, always you can find all the 2D materials, even if you do transport calculation or adsorption calculation as well, they are sensed towards nitrogen dioxide molecules. So yeah, very interesting results. So what I found in my PhD. but you can also try to, add on different types of 2D materials, and you can set up the devices for all these three different applications. Yeah. The next topic that you see on the left hand side, the image, I think in the childhood you might have done this. So when you rub a comb on your hair and try to identify some of pieces of paper, try to attach them, so you can see that's called static electricity. So this term has been developed by Professor Zhonglin Feng, and he is one of the pioneers in triboelectric nanogenerators. This is one of the applications from the contact electrification application. So yeah, so I use this technology on different 2D materials. I have taken aluminum nitride, gallium nitride, and silicon to understand the mechanism of solid-liquid interface. So in a solvent system, if you put the 2D materials, all these 2D materials, so what kind of effect that you are going to get? So I think in the solvent system, I mean, in different types of, if you put these 2D materials for one of the applications in triboelectricity, so it has a silicon has been quite widely used, and you can see there's different molecules, they are present in the water, like NaCl, oxygen atoms, and different all different kinds of chlorine atom. And you can see that I have used a combination technology over here. On the upper hand side, what you see is density functional theory, where I did some total charge transfer calculation, beta charge calculations. And in the right hand side bottom corner, what you see is based on classical dynamics approach, where you can devise these kind of 2D material setup under a solvent environment and try to identify what type of adsorption principle they have for different 2D materials in solvent environment. So in this case, what you can see based on the lab's results, that chlorine is much more prominent on gallium nitride in comparison to other different types of 2D materials. So this is very interesting applications, and you can find the paper on solid liquid interface, which has been published in Nanoscale Advances. And yeah, this is one of the applications of contact electrification. So this is a basic application to understand the mechanism of solid liquid interface. But when you go for different types of applications, so you might have heard that gold nanoparticles, 2D materials, or even the clusters, they are widely used for different biological applications. So gold is one of the most powerful agent in drug delivery. So how it interacts, I mean, how can you devise such platform to understand different types of molecules, micromolecules inside your body, how they interact with the gold setup, or the gold nanoparticles. So this is a classic example where I've done molecular dynamics simulation using GROMACS to understand how these molecules, they get interacted on the surface of 2D materials. So this paper is not yet published, but I'm soon going to publish this paper. And you can see that these device setup can only be used when you use classical dynamics approach. And even in CSI also you can devise this, but it might take some time. But if you use lamps or if you use GROMACS for this kind of setup, then that would be really fantastic. Coming to another application of contact electrification. So you know that in power transformers where the electricity generation happens, nowadays they are using cellulose materials, and these cellulose materials are quite a good insulating agent. So so this project has been sponsored by Hitachi from here in Sweden, and they try to understand how the molecular interaction between different types of oil molecules used in power transformers, like naphthenic compounds, aromatic compounds, and paraffinic compounds. And they want to understand how these cellulose materials behave when exposed into different oil conditions. So as you can see in the left-hand side, that paraffinic compounds, they kind of form different types of clusters. So these oil molecules, they form different types of clusters. And this has been achieved by doing molecular dynamics simulation using GROMACS. And this setup you can use it from charm force field. If you know about classical dynamics, then you might have known about charm force field, and this can be utilized to understand the solid-solid interaction interface. So this is quite a popular. This paper has not been published yet. This is under preparation, and I'm soon going to publish this paper so that you can know more details how I have done this. So this is not possible in density functional theory calculations. You have to use classical molecular dynamics. Okay, the next topic is very interesting to me. This has been supervised by Professor Yogendra Mishra from Southern University of Denmark. And this topic concerns about 3D materials. As you can see that the animation that you see is typical structure of zinc oxide tetrapores. And it has a very complex architecture, like it has 4 arms and it attaches to a central point in zinc oxide tetrapores. So this is a very good antiviral agent. So one of the patents that we have done is this particular cream has been used for antiviral therapy. So whenever you get herpes virus, HSV1 is very common in world. So if you apply zinc into that particular viral agents or infection, it can be cured within days. That's the power of zinc oxide. And you know that human body contains almost 30% of zinc. So zinc is very necessary. So it is a very good agent for antiviral agent. So what you have done in this work is we have taken zinc oxide tetrapods and coated with the different types of gold nanoparticles. And we just want to identify that whether this functionality of zinc oxide tetrapods remains the same or the bare zinc oxide tetrapod has more activity. So what we have found is when we try to identify the interaction between different types of macromolecules from herpes simplex virus, and we can see that the zotin itself, the zinc oxide tetrapod itself, has high efficacy towards antivirals in comparison to the functionalization of the zinc oxide tetrapods. And during the pandemic, I also tried to understand how the interaction of zinc oxide tetrapods with different types of viruses, and it is a very good agent for SARS-CoV-2 as well. So this can be a part of research, and this has been submitted in antiviral research. I think it will be published soon. So you may find, and this is a combinatorial technology of DFT. You have to construct zinc oxide tetrapod architecture by using density functional theory. Then you use, bioinformatics analysis like classical dynamics and classical molecular docking analysis to understand the interaction between different macromolecules. And if you use nanomaterials, you can use that as well. And this is a patent that we have filed, and I just want to show you some of the examples that whatever the things that we're doing in research in vivo. In vivo, it means we are using different organisms to understand how the nanomaterials interact. So this is a typical example of zebrafish embryos, which we used to study the interaction of zinc oxide tetrapods. So the arrow marks that you see, whenever it enters into different types of embryos, it stays on the surface. So if you put zinc oxide nanoparticles instead of zinc oxide tetrapods, then it might enter or invade different cellular layers, and it can cause reactive oxygen species and apoptosis. But zinc oxide tetrapods is a very nice toxic agent, I would say, and it gives less cytotoxicity to the cells instead of nanoparticles. So whatever the nanoparticles use, I'll show you one typical example of nanoparticles, that is silk nanoparticles, that has been used to study this kind of interactions. Yeah, and I just want to mention that whatever the results that you see on the surface of it, we just try to understand by using classical dynamics, using lamps, to study that whether these tetrapods, they remain attached when you cut off the arms in a solvent environment, and to see that whether these arms are getting attached again or they have been detached in the same form in different water environment or the solvent environment. So yeah, this is a peculiar study. As you can see, when you cut off the 3 legs and try to simulate for more course of simulation or a longer time period of simulation, you can see that these arms are getting closer to the central point of syncope-side tetraphores. It's a very nice and peculiar results that we found, and I think this is widely applied in practical scenarios as well. As I mentioned that, I just want to show you how these nanoparticles, they invade into the cells. And by using a combinatorial technology that is from DFT, as you can see from the left-hand side, these are silver nanoparticles. These are modeled by using density functional theory, and you can see total energy and the dynamics, how these nanoparticles, they behave in vacuum. But when it comes to the in vivo organisms, how these nanoparticles, they invade into the zebrafish embryos or the any particular organism, how they invade into the cells. And by using classical dynamics and technology, we can see that these are interacting and they induce a lot of reactive oxygen species and apoptosis, which might eventually kill the organism or kill the cells. So these nanoparticles are very, very toxic sometimes, but sometimes these nanoparticles, they do have a peculiar property without having any toxicity or cytotoxic to the cells. But in our case, it is quite, we have seen that this nanoparticle, they induce some kind of toxicity to the cells. And yeah, that's it. I mean, these are the 3 topics that I have covered. I mean, much more I have covered in my PhD, as you can see from my different papers. But I would like to thank Professor Y.K. Mishra, Jonglin Wong, Johan from Karolinska, Mrutyunjay, and Rajiv from Uppsala. And these are my colleagues who helped me to understand this concept, to frame the ideas, and to get some insights into biological perspective and from quantum physics perspective as well. Yeah, thank you very much. And you can watch my YouTube tutorials on Siesta, and you can combine both Dr. Verma's and mine YouTube tutorials to understand how the transport happens. I have a tutorial on the on the setup of different transport system, and you can find a detailed tutorial on that. So yeah, you can reach me out anytime, and thank you very much.
Now session is open for discussion. If anyone has any question, then you can ask.
Dr. Panda, it was really very attractive and wonderful lecture. Thanks for
Thank you.
Accepting the invitation from this organizing committee. And a simple question related to that computational time. That compared to SISTA, the computational time of GROMEX is how you compare?
Very less. Very less.
So
yeah, and you can deal with the billions of atoms.
Okay, so it's easy to learn. I think I have the.
Yes, it's kind of easy to learn. Yeah, of course.
So we should suggest some others to do molecular dynamics simulation using.
Oh yeah,
this GROMEX.
yeah. Please. I mean, if you combine density functional theory with classical dynamics, either by using LAMPS or maybe using GROMAX, that would be fantastic. That will give you a very nice overview of any of the results that you do, including 2D materials, including nanoparticles, or anything. You can do anything. So I have done recently published during the pandemic paper in Science, and I have used extensively molecular dynamics on that by using GROMAX.
Thank you.
Hello, Sir Panda. That was a wonderful and thought-provoking talk, as I would say. I have few questions, like if I can frame it out.
Yeah, please.
Yeah, like you talked about the K-desorption and P-desorption process, no, sir? Can we go back to that one? like I saw the binding energy, like there was those two binding energy were of the nearly of the same order, no? So how did
Yeah.
you distinguish that one as FPG absorption process and another one as the chemical
Yeah,
absorption
exactly. Good question. That this question has been asked by many experimentalists, and I would say this has baffled me as well when I try to implement this method to understand how the physics option, the chemistry option works. So again, I have not shown one of the results because that one I have done by using molecular docking technology. Okay, so when you put the molecules on the top in Siesta or in WESSM, when you take 2D materials and you put different types of molecules, those are based on distance-based methods. You randomly put, or else what you can do is you can do nudge elastic band calculation, NEB calculation.
Yeah, NEB calculation.
Okay, and you find out a common minima where the molecules is having a least energy or the lowest energy.
Yeah.
Right, and sometimes you see highest energy. So the highest energy point where in the 2D material, wherever you see, those are chemisorption states because they have a highest energy point. But whenever you see a lowest energy point that has been, quite favorable for 2D material, that might be the case for the physics. I mean, you have to check. It depends on the molecules and depends on how big is the molecule. So one of the key approach is NEB calculations or nudge elastic band calculations.
Also, can we take into consideration the charge transfer mechanism also, like how much charge has been transferred from the molecules and all?
Yes, absolutely. So in my case, in terms of nitrogen dioxide, when it was absorbed on a specific molecule called TPDT, triphenyl diethyl, so you can see that it forms a extra bond. So that extra bond is another way to understand the physics option and chemistry option is work function. If your work function is high, that means it is. If your work function is high, that means it is very the very much energy is required to extract the bonding from that. So that's a typical example. If your work function is high, that means it is inclined towards chemistry option.
Okay. Yeah. And also, sir, how did you design the solvent models, like those solvent models? And
the solvent model.
How did you take into the consideration of those different atoms? Like how did you design the force field potential also? Like it's not all available in the literature and all. No, like how those two molecules interact and all.
Yeah,
like
I would like to. I would like to tell you my secret. Why I have been using this. So you can use CHARM GUI. CHARMM, CHARM GUI. That's a very good platform to design materials for molecular dynamics simulation, which is based on 2D materials. You can design. So that's the platform. You go and the potentials have been defined there. So you don't have to do anything. You don't have to define any potential. You just directly go there and click on the 2D material that you are interested, and that's it. You can do that.
It will directly take into the consideration all those
absolutely.
parameters.
And I have a tutorial on that also. So you can check my molecular dynamics tutorial.
I'll go through that one.
And if you follow my if you follow my GitHub channel, okay, there also there is a section called molecular dynamics, and you can see I have mentioned a protocol for nanomaterials also, like the cellulose materials that I've shown. I have a protocol for that, so you can also do that. And I'm also going to make some tutorials. I'm quite busy with my 3-month-old son. Recently I became a father, so
that's a good news.
So
too much occupied, I think so.
Too much.
Also, sir, last question, sir. Like, what kind of approximations you took into the consideration? Like statistical approximation. We have to, when we do this molecular dynamics and all, like we have to keep the system on the heat bath, like NCT, NVT, and all. So
that has been well defined. That has been quite well defined in CHARM GUI, and one of the tutorials from Justin Lemkul. This is the guy who developed this molecular dynamics. And for your knowledge, the Gromax is developed in Uppsala University. You know that?
Yeah.
So I'm fortunate enough to work with one of the founders of Gromax, who is known as David van der Spoel, here in Biomedicine Centrum. So yeah, you can follow the tutorials from Justin Lemkul. I have shown in my video also, in my YouTube video also. You can follow the tutorial and the approximations for ergodicity. You say as ensemble averages like NPT, NPT. So that you can take, you follow the same tutorial. You don't have to change it. Just follow the same. And it has been maintained at 300 Kelvin. That's the temperature, typical temperature that we take to equilibrate the system.
Thank you, sir.
Thank you very much, sir.
Thank you, sir. Your talk on electronic transport at a nanoscale and nanomaterial complex architecture. It will definitely help our participants on research area. Thank you, sir.
Thank you very much. Pleasure to have you all. Thank you very much.
I would like to invite Dr. Manisha Gupta ma'am to introduce Dr. Manvendra Tripathi sir for next talk.
Hello everyone. I am Manisha Gupta from Government Nagarjuna PG College of Science, taking the honor to introduce Dr. Manvendra Tripathi sir. Dr. Tripathi presently working as Associate Professor in Metallurgical Department in NIT Raipur. He has done his Masters from IIT BHU and PhD from Indian Institute of Engineering Science and Technology. His research fields includes compositional design, bulk metallic glasses, welding technology, material characterization, and corrosion engineering. He has many publications in international research journals. Now, I invite Dr. Manvendra Tripathi sir for his talk. So please welcome, sir.
Thank you, ma'am. Can you please confirm that it is audible?
Yes, sir, you are audible.
Okay, so at the outset, I thanks the organizers, Professor Anjali Awadhya madam and Dr. Mohanlal Verma madam and all present here. And it is my pleasure to be part of this. And due to certain constraints, I'm not present here. I have to take this lecture in online mode. So please confirm that if my slides are visible. Can you see my slides? Oh, I'm sorry, I have to present it, right? So please give me 1 minute to share my screen. Whether my slide is visible?
Yes, sir. Perfectly visible, sir. Please enter full screen mode.
Yeah, sure. Thank you very much. So actually, today's discussion which we are going to do is it is synthesis and characterization of multi-component alloys. And so whether the heading is also visible, the evolution of metallic material.
Yes, sir. Yes, sir.
Okay. Okay, evolution of metallic materials. So on this slide, actually, if we have a look here, that on x-axis it is the timeline, and on the y-axis it is the relative importance of the material. So it is a very perfect slide, basically, to tell you the importance of the various metals. So if you can follow my cursor, so 10,000 years before Christ, it was Stone Age, then we entered into the Bronze Age, then the Iron Age, then the Age of the Steel. So if you look at the Age of Steel, so it was somewhere around 1800 to 1900 or so. And later on, it is the age of the polymers, now the age of the silicon. So if you look of the age of the polymers, it is around 1960 to 1980, and age of silicon, it is around 1990 or so. And now, the concept of so-called high entropy alloys, it is the new words which have been coined recently. Now, if we go to, another term which you will see here is the age of molecular engineering first. And second is that I have attempted to understand this slide basically, so it appears to me that the area covered here, that tells you the importance of a particular metal first. And you see that it is about 60% area. So if we talk about the materials being used for the household purpose, or let us say for industrial purpose, metallic materials, they still dominate first. And second is that the pure metallic materials, they are rarely used. It is used in alloyed form. So the question comes that what is the purpose of alloying? So if you put two metals or more than two metals together, so it is giving you a different property than its original metal. Pure metal, if you work with the pure metal, so the property is going to change. So it is important basically, like if you look for industrial applications or for household purpose, so metallic materials and their alloys is important. And this image, it gives a clear picture actually of the use of the metallic materials, right? So now, like for example, the gold, copper, and bronze, cast iron, steel. Steel is also an alloy steel, the light alloys, super alloys, titanium, zirconium, all these alloys basically now. And aluminum, lithium alloy, dual phase steel, microalloy steel, and all these metallic materials and alloys. So the concept of alloying is necessary, very much important. So what we are going to do today is that we are going to enter into the finer thermodynamic aspects of whether the metallic alloy will form or it will not form. Means formation and its stability, we are going to enter into the detail, and little bit we'll touch upon the characterization, the primary characterization techniques which are used for the metallic material. Let me go to the next slide. So it is the metallic material. The heading of the slide is metallic material in everyday life. So you must be familiar and aware that we use steel-based material, and this steel-based material, it is used for various purposes. Then again, that aluminum-based alloy, they are also very popular. Copper-based alloy, next is chromium and nickel-based alloy, and various electronic applications such as computer disk printed circuits and connectors and switches. And even that in the human body, as hips and knees replacement, we use metallic material, and surgical plates and screws and wires. And so and coins in our daily commerce and the jewelry. So whatever I have covered here, it is very small number basically, but just to connect with that, we are using our metallic material on day-to-day life basis, and it has industrial application. Now I'm going to in the very basics, very fundamentals, like state of the matter. So I'll say that in +2 level we discuss about ideal gases, that is PV equal to nRT, right? But if we talk about the materials, and if this ideal gas concept, it is not good enough, we need to understand there is something called real gases. And in real gases, that there is interaction among the molecules, which is not present in the ideal gas. And then, if these interactions, they are going to increase, then it starts behaving like liquids. And once this molecular interactions, atomic interactions, it is going to increase, it starts behaving like solid, right? So this is the state of the matter. And if we want to understand the line behavior, so obviously, that we have to understand that if it is in solid state, how it will behave, it is in liquid state, how it will behave. Rarely we talk about the gaseous state, because solid liquid, it is good enough for us for the practical purpose. But the actual journey, it starts from the ideal gas to the real gas to the liquid and to the solid. So we'll try to cover this continuum basically, right? Let me go to the next slide. So somehow I'm unable to see the heading, but anyway, if I look at this plot, so it appears to me that the left hand side, it is the pressure and volume. And for example, we are trying to plot the PV equal to nRT. So this plot is taken for the ideal gas. And if you take any ideal gas and if you subject it to the fairly high temperature, that is 1000 Kelvin or so, so its behavior, like it is going to behave like, it is going to obey PV equal to nRT. So it is behaving, it is obeying the ideal gas equation. And here, that Boyle's law and Charles law, that basics I'm speaking here. And here, if you keep the pressure constant, okay, so the volume and temperature, they are linearly related. So Boyle's law and Charles' law, we have studied in the even class 9, 10th, 11th, 12th, we have studied it, right? So this is what in that this conception we have very high clarity on it. But the point is that like there is a departure from the ideal behavior. So like again I am taking the pressure, and you can consider here as volume on the x-axis, and if I'm writing it molar volume, so molar volume is nothing but you take a gas of 1 mole, right? So, and whatever its volume is, it is referred as molar volume. So here that if you take a high temperature, so this T1 temperature, let us consider that it is high temperature. So this gas is behaving like an ideal gas. That is parabolic relation or hyperbolic relationship is there. PV equal to nRT. That kind of behavior is observed. But let us do an experiment. That experiment is conducted. What if that we continue to reduce the temperature? So if you are reducing it slightly, that the shape is not going to change. But again, if you are going to come to the temperature T3, so there is slight deviation, slight changes over here. And whenever this slight changes there, so it is a signature that the gas, it is departing from ideal behavior. So as we decrease the temperature, right? Let me take the example of LPG. What is that? Liquefied petroleum gas. So the gas can be liquefied, right? But you have to give the suitable condition. So what is the suitable condition? You increase the pressure, it will liquefy. Or if you decrease the temperature, it will liquefy, right? Means this is the initial notion. But here I'm going to introduce you the concept of critical temperature here. So as we continue to decrease the temperature, this is referred as a critical temperature, where there is a horizontal point, and it is referred as point of inflection, basically, right? So at this temperature or below it, it is quite possible. This is the reason of the liquefaction. Let me take the temperature T8 or so. So here it is in gaseous state, but at this point, it is becoming horizontal, and here the first liquid has formed, right? So what we are doing is that at relatively lower temperature. Can you please mute? Yeah. So let us continue. So at low temperature, at when the molar volume is this, that if you permit higher molar volume, it is behaving in a gaseous state. But as you continue to compress it, so it is transforming into liquid. And here that if you refer my arrow here, so it is combination of liquid and gas. So if what we are doing is that you put the gas in a container and you continue to compress it. So due to compression, the liquefaction is increasing. And if you reach to this extreme C, so complete gas, it is converted into liquid. Now, if you want to further compress it, right? So you have to apply a lot of pressure basically in order to compress it. So here, this is the temperature, which is the critical temperature. So it is referred that if you want to liquefy any gas, you have to be at this temperature or below it, right? And above this temperature, you cannot liquefy. So this is the concept of critical temperature first. So your question, a question will be coming to your mind that we are trying to understand the alloying behavior basically. Yes. So why we are talking about the real gas? See, I'm talking about the real gas to give you a sense, that the ideal gas, it is just a concept basically. If it is not real. So what is real? So real is the real gas or the liquids or the solids basically, right? So what makes it real, right? That is the next question. What makes it real? So the molecular interaction make it real, as simple as that, right? And molecular interaction, and I'll say that it is the attractive forces that make it real. And and as I said, that there is a continuum from the ideal behavior to the liquid, to the real behavior, to the liquid, and to the solid. All right. Can you please confirm that it is audible?
But the slide is not visible, sir.
Yes, sir. Yes, sir. Audible, and sir, your slide is also visible, sir.
Oh,
okay, fine. Let me go to the next point. Because I have received a message that my internet connection is not stable. That is why I'm asking. Let me go to the next slide. Okay. So now that deviation from somehow on my screen.
Due to network problem, sir has left. He will rejoin soon.
Is it connected?
Yes, sir. Yes, sir.
Yeah, I'm trying to share my screen,
Okay.
but host disabled participant is screen sharing. Can you please help me to share my screen?
You can share now.
Yeah. Okay, so let us continue. I'm really sorry for this interruption. You confirm that you can see my screen? Can we continue? Can we proceed?
Yes.
Is it audible?
Yes.
Okay.
Yes, sir. You are.
Yes. So we were talking about deviation from the ideality. Okay. So there is something called referred as compressibility factor. Let us define it as a Z, and Z is nothing but PV by RT. Okay. So and like let us assume that the gases, they behave in ideal manner. So PV by RT, if we define it, so for 1 mole gas, its value of the Z should ideally be equal to 1. But if we plot here Z with respect to the pressure, for example, that what is happening to the Z if we increase the pressure. This is what we are trying to understand. So that ideally it is supposed to be a straight line, a horizontal straight line, but we find that there is a departure from the Z. So this is another proof that that the gases, they behave in a real basis, they don't behave on the ideal basis. And so let me go to the next slide. So Z itself is function of pressure and temperature. And this plot it is plotted at temperature 0 Celsius. When temperature 0 Celsius is kept, and if you are just wearing the P, so Z is changing. And that there is a departure from the ideality. That is the second proof. Let me go to the next point. So this is the periodic table basically. And that I'm showing here is that we are limited by the number of elements. For example, 100 plus elements are there. So if there is no alloying and there is no mixing, so we should have been limited by the very less number of the elements present. But now the next question is, what if I take chromium in some proportion, let me say 20% chromium, and I put it in manganese, whether it will mix and mix. For example, if it is in liquid state, whether it will mix or not, and if you put it in solid state, whether it will mix or not. So these are the questions. These are not simple questions. These are the challenging questions, and proper thermodynamic protocol has been developed for it, right? So let us have a look on it, right? So in order to enter into the subject, what the simplest thing which comes to my mind is that there is something called phase equilibrium of one component system. So I guess that you must be familiar about this phase diagram. And here, that we are working with one component system. So what is component, will define it. But here we are working with the water system. So as you understand that in this pressure temperature region, it will be in ice form. Here it will be in a liquid water form, and here it will be in the gaseous form, right? So one thing we can learn from here is that the pressure and temperature, these are the important variables. If you are going to change the pressure and temperature, then the state of aggregate, whether it is gas or the liquid or solid, it is going to change. This is one point. Second point is that for sake of simplicity, we are not varying the composition. We are taking the composition of water, that is it, and this we refer as pure component. You are not going to mix anything with it, right? Because if you are going to mix anything with it, it is going to increase complexity. That is why we are referring to it as a pure component system. But if we want to understand the alloying behavior, then we have to learn about the mixing. That keeping it so simple, it is not going to work. Let me go to the next slide. So here, that here it is the equilibrium of the solid and liquid. So this is solid and this is liquid, and this is the interface, right? So if you are at this line for that pressure temperature, solid and liquid can coexist. Similarly, here at liquid and gas, it can coexist. And here, solid and gas can coexist at this triple point. It is referred as triple point. Solid, liquid, gas, it is going to, that all these three states, it is going to coexist. Now, what is thermodynamic components? So components are chemical species with fixed composition. This is how components are defined. So let me take example of water. Let me go to the previous slide. So here we are referring that it is one component system. It means that there is hydrogen and oxygen, but this hydrogen and oxygen, bonded properly, and this bond is not going to break. That is why we are referring it as one component. So we need to understand the word component properly because we have to use it very frequently in the coming slides. Let me go to the next point, that is the simplest components are the chemical elements and the stoichiometric compounds. This is another simplification we can understand, right? And initially we'll talk about binary system, but two component system. Then if you understand the thermodynamic aspect of the two component system, so you can easily extend it for three or more component system. So it become we refer it as multi-component system, right? So now one component system, it is normally referred as unary system, two component system as binary, and three component as ternary, and four component that is quaternary system. So initially what we'll do is that we will discuss about the binary systems, that if you're going to put two components together, so how they will interact with each other, right? Whether they will mix or they will not mix, and that we'll proceed ahead with. So let me go to, there is something called phase, and I guess that you must be familiar with the term phase. So a phase is defined as being a finite volume in physical system within which the properties are uniformly constant. This is what it is expected, and it do not experience any abrupt change in passing from one point to another point in that volume. So sometimes we refer phase as they are physically distinct from the surrounding, chemically homogeneous, and mechanically separable. These are the three conditions which we apply on the phase, actually, right? So within any of one phase area, the phase in so-called phase diagram, the system is said to be homogeneous. Okay, and that a system is referred as heterogeneous when it contains two or more phases, right? So for example, the coexisting of ice and liquid are very frequently we refer about liquid and ice, because it is easy, because we are all familiar with the liquid, ice, and the vapor and all. But in the metallic system, gradually we have to switch over to metallic system, and it's mix or it's along basically. So we refer it to heterogeneous system comprising the two phases or maybe three phases also. Now what is phase diagram? Phase diagram we all know, but we are formally defining it. It is a graphical representation of equilibrium states of the existence of a system, right? And the constitution, or the phase diagram is most popular and the convenient. This is equilibrium states, So now the question is, what is the meaning of equilibrium state? So here, that if we want to understand equilibrium, simple equilibrium, so you take a container, okay, and you put a gas into it, and it is frictionless container. So, if the pressure of the gas is more, this piston is going to go up. If the weight is more and the pressure is less, it is going to go down. So we refer that it is not in equilibrium. But at equilibrium, this piston is going to remain static, right? So this is the example of mechanical equilibrium. There is a possibility of thermodynamic equilibrium, for example. It will be in equilibrium given that the pressure on this piston outside and inside it is same, and temperature of gas outside and inside it is same. So this is referred as equilibrium, and this is important. This condition is important if you want to understand the mixing of alloy. Now the combined statement of the first law and the second law. So I assume that all of us know that first law, that is equal to delta Q equal to du plus delta W, right? And strictly speaking, it should be delta Q reversible, right? And if you do a process very, very slowly, we say that we are doing it reversibly. And if you do it fast enough, so we say that we are doing it irreversible. So, in order to explain what is reversible and irreversible process, it can take about 60 minutes discussion. So I'm not going to enter into it, and I have to bypass it, right? And, normally we define ds, that is equal to dq reversible by t. This is referred as the second law. What we are doing is that we are going to put these two statements together. So dq equal to tds, right? And so we are going to replace it here. And if you do it, so du can be written as tds minus, in place of t, change in the mechanical work, we are referring it as pdv. But if you want to generalize, you can put the electrical, magnetic, and other forms of the work also. So what we are doing is that we are putting first and second law together. So du equal to tds minus pdv, and that this will become conditional equilibrium. Du, if the du is 0 for a given system, and you are treating the entropy and the volume as primary variable, and given that it is a closed system, then that becomes a conditional equilibrium. And if the du becomes negative, okay, I'm not going to go in this inequality condition. So in order to define that it is inequality condition, so I have to tell you the difference between reversible and irreversible. And if we understand that difference, then this equality sign will convert into less than or equal to. So if du becomes less than something, then it becomes a spontaneous process or irreversible process. So you don't need to apply any external force for that process to continue, right? So, so these are the conditions of equilibrium, right? So let me go to the next slide. And next slide is that this is not the only condition, d equal to TdS minus PdV, but like we can write it in terms of ds, that is equal to TdS plus VdP, and dA, that is Helmholtz energy, that is equal to minus SdT minus PdV, and dG, that is the change in Gibbs energy, that is equal to minus SdT plus VdP also. But so these are the four conditions of equilibrium, and they are applicable under different conditions. For example, we will apply this condition in equilibrium given that S and V is primary variable. We will apply this condition given that S and P is the primary variable. This condition when the temperature and volume is primary condition, and this when the T and P, it is a primary variables basically. And that the third, and these are not only two terms, there will be a third term also required if you talk about the open system. This condition of equilibrium, it is valid for the closed system, but that if we go ahead and we can understand what is the idea of the open system. Now, variation of the composition and the size of the system. So let me go to the next point. Now the point is that Gibbs energy, right? It is a function of temperature and pressure. And additionally, we need to learn that it is function of the composition also. So this is the ith component, this is the jth component, and this is the kth component. So if given that it is that the system is having three components, so I, J, K. So it is not only function of pressure, temperature, but it is function of composition. This is the primary point. Now, if you do partial differentiation, it will appear like this. So you differentiate it with respect to T, keeping the pressure and the composition constant. And this is not small t, it is that typographical error. It is the D and capital T. Capital T means it should be in terms of temperature. Similarly, you differentiate it with pressure, right, and keep the temperature and composition constant. Similarly, if you differentiate it with respect to one particular component, so you have to keep the pressure, temperature constant, and other components constant. Similarly, you have to differentiate it with Z component, like that. So this is the partial differentiation we have done, right? Now the point is that we know that dG is equal to VdP minus SdT. We have derived it already, right, in the previous slide. So like if you compare this equation and this equation, you can find that with dt term, this term is appearing, right? So this term is as good as minus S, dou G by dou T, keeping pressure and this composition constant, that is equal to minus S. Similarly, if you compare it with respect to dP, right? So this term is as good as V, okay? That is the molar volume. So let us say, so dG by dP at keeping temperature and other this constant. So this is the molar volume. So, and so what about the third term? The question comes that what about the third term and the fourth term? So the point is that we need to introduce the concept of chemical potential. So that this term, so like the first term and second term, we are writing it like this, and the next term, this will be referred as chemical potential of the first component, ith component, and this will be dNi. And that this I is going to run from 1 to k. If given that there are k terms, you are going to put them together, you are going to mix them together. Okay, so we'll understand what is the idea and what is the notion of mixing. Okay, so like we have already understood that this term is effectively behaving like, and we refer it as in terms of mu, and mu of the ith component, right? So here the G is expressed as function of pressure, temperature, and the G is this is expressed in terms of pressure, temperature, and composition. Let me go to the next point, right? So now this is the generalized equation, right? For example, if I write dG equal to VdP minus SdT, this will work only for closed system. But the moment you are going to add this, so it will work for the open system also, right? So, and now so I'm saying that what is the notion of the heat capacity? This is the relevant aspect of the story, and I understand that those who are present here, they understand what is the heat capacity at constant volume. It is referred as the change in heat per unit temperature, keeping the volume constant, right? And similarly, this is heat capacity at constant pressure, change in heat, or like, and with respect to change in temperature, keeping pressure constant. This is how Cp and Cv is defined. Now, like, let me introduce that there is an energy E, and if you multiply it with the number of moles, so we are referring it as E prime, right? So this is extensive property, and this is referred as intensive property, basically, right? So if you divide total energy by the number of moles, so that energy starts behaving like an intensive property, right? So what we need to do is that we have to have clarity that whether we are working with extensive property, and if it is extensive property, it has to be multiplied with number of moles. We have to be clear about it. So the du prime that is equal to its heat capacity into dt, and heat capacity cv can be written as ncv, something like that. So now we can write du, and du stands for the change in internal energy per mole, that is equal to cv dt. Similarly, we can write dh is equal to cp dt. So change in enthalpy, that is equal to cp dt, right? Again, the point is that change in enthalpy can be, we can calculate keeping pressure constant, and if there is change in temperature only, right? So it is, you have to do integration both sides. So integrating it of cp dt from T1 temperature to T2 temperature, you can find out what is change in enthalpy. The question may be coming to your mind that why we are going into such details. Basically, the point is that at the end we need to find out the expression delta G is equal to delta H minus T delta S. Now, so somehow if you can find out what is delta H and what delta S, so you can find out delta G. Now the question is that what we'll do if we find out delta G. Delta G equal to 0, that will say that the system is at equilibrium. Delta G is negative, means if you write about a process and for a process delta G comes out to be negative, that process is going to happen spontaneously. So which process we are interested in? We are interested in finding out whether two elements, they will mix together or not, and what are the conditions under which they will mix, means at which pressure temperature they are going to mix, and when they will not mix. This is what we want to understand. So this is referred as the alloying behavior, right? So we need to understand a bit of alloying behavior, right? And so we have to connect it with phase diagram. Then once your material is synthesized, then how do you characterize it? We'll discuss it in very short, right? So I'm just trying to give you in an overview, right? If we get into the details, it will take a lot of time. So better let me give you an overview, and if you have any question, feel free to ask me the questions at that, right? So empirical representation of the heat capacity. Without getting into the detail, let me tell you that heat capacity, it can be experimentally, you can find out ABC for a particular component or for a particular material, and we do DSC, differential scanning calorimetry, using which that how CP varies with temperature. CP is not constant, let me tell you. It depends on temperature, right? So the molar heat capacity of a substance or material, it depends on temperature, and normally it is represented in this equation form, polynomial form, and ABC, it depends on the particular material, right? Now, I'm taking an example that alpha of ZrO2 is a material, and it is having a particular crystal structure which we are referring as alpha crystal structure. So its CP is like this. So you can understand that the value of A is this, value of B is this, and value of C is this, something like that. And this is the unit of the CP. And but this CP is not valid in general. It is valid in this temperature range only. But the moment you are going to cross this temperature, so there is transformation. This material itself is changing, and it is behaving as a new phase. This was one phase, this is another phase. Now the CP, somehow it becomes constant with respect to temperature. Now it is not functional temperature. But the point is that what I want to convey here using this slide is that it is possible for that to find out the function of CP, the dependence of CP with respect to temperature for a given material. Okay, and if we know the CP, so it is quite possible we can find out what is the change in enthalpy and what is change in entropy. And by knowing this, you can find out what is change in the Gibbs energy, right? This is what we want to understand here. So now the variation with temperature of the constant pressure and molar heat capacity. Now this is graphical representation, that if you are changing the temperature, how the heat capacity is changing. So please see here that if you refer here, this is how the alpha ZR, the CP is changing with respect to temperature. The point is that don't assume that CP is going to remain constant with respect to temperature. It can vary with respect to temperature first, and if there is phase transformation, so CP can change basically. So here at this temperature there is phase transformation and new phase is forming, so CP is changing. And actually CP contains the information of the bonding process in a particular material. Let me go to the next slide. So enthalpy as a function of temperature and composition. So we have seen that if you want to find out change in enthalpy, so you have to integrate CP dt. So if you have the expression of CP and if you integrate with respect to temperature from T1 to T2, so you can find out change in enthalpy. So the point is that finding out change in enthalpy, it is very easy task. It is not a difficult task. But if somebody is referring that I want to know the absolute value of the enthalpy, there is certain difficulty. So you have to take certain, some reference level you have to define and you have to go for it, right? So again, that there may be question that what if that A and B, they are going to react and they are going to form a compound AB. So what will be what will a change in enthalpy? So change in enthalpy it is referred as the enthalpy of that compound AB at given temperature, pressure, without changing the temperature, pressure, minus. You have to take the enthalpy of the A and you have to take the enthalpy of B, you have to subtract, so that this is going to give you a change in enthalpy, right? And that enthalpy, it is an extensive property. So like it is 1 mole, 1 mole, and 1 mole. It is not necessary. It can be 2 mole, 3 mole, and it can be 5 mole. So what we have to do is that we have to multiply these enthalpies with the corresponding moles. So because it is an extensive property, this is the care we need to take. And this is like how the enthalpy enthalpy of a substance, it is going to change with the zero temperature. It is referred as enthalpy temperature diagram. Will not go into the details. If very much required and if you are very much interested knowing it, will come to it once again, right? So again, like this is enthalpy temperature diagram. Let me tell you is that how enthalpy is going to change for when it is in solid state. So obviously you need to know what is the CP value, and how the enthalpy is going to change in the liquid state. You need to know the CP value when that substance is in liquid state, right? And if that Kirchhoff rule, it applies that if you are moving in this entire circuit, right? So change in enthalpies, some delta of the changes in enthalpy are going to join, so it will come out to be zero. So all these calculations, they are useful, right? So but I'm not entering into detail. And now like let me go to the what is yeah. So enthalpy temperature diagram, I'm bypassing it, in order to save some time. Let me bypass it. And now the conventional enthalpy defining the reference state. I guess that you must be knowing that as H does not have any absolute value, right? Only change in H can be measured. So it will be convenient to introduce a convention which will allow, refer it, please mind it that it is just a convention, right? So convention which will allow the comparison of different enthalpy temperature diagrams, okay? And now the convention assigns the value 0 to the enthalpy of the element in their stable state at 298 Kelvin. And like if you want, you can say that it is pressure is also defined. It is 1 atmospheric pressure, but the rate of change of enthalpy with respect to pressure, it is almost 0. So even if you don't mention here pressure, it's okay. So this is how the enthalpy is defined, right? Now how the enthalpy of compound is defined. So again, there is a protocols to define the enthalpy of protocol. This is how the enthalpy of a compound is defined. I'm not entering into the detail. I'm just giving you an overview that how the change in enthalpy and how the change in entropy, it can be actually calculated by thermodynamic protocols, and how it is connected to the phase diagram. And these phase diagrams, that will tell you whether two elements, they will mix or not mix, and whether you will get an alloy or not for a binary system. And once you understand the concept of the mixing of binary system, you can understand the concept of, let me say, that 3 component or more component system. Okay. Now, like how the dependence of entropy on the temperature. So this comes from the second law, ds is equal to dq by t also, right? So again, that if you are doing the process of constant pressure, so dq can be written in terms of dh, okay, and dh can be written as cp dt by t. Okay, so if you now you integrate both sides, so the integration, it will give you the change in entropy, and here integration again. So like cp, it is constant temperature, so cp dt by t. If you are going to do this integration in the proper limits from t1 to t2, similarly s1 to s2, so you will get the change in delta. So this is what is required to find out your delta g. And what is delta g? That decides, like if you are going to treat pressure and temperature as primary variable, so change in Gibbs energy, if it is 0, your substance will be in equilibrium. If it is negative, so for a process it is negative, the process will be spontaneous, something like that. That is why we are talking about it. So this is how delta S is defined, and this is how you are going to integrate it. Let me go to the next slide. So that dependence of the entropy, dependence of entropy on the temperature. So S minus S naught, that is integral Cp dt by T, and S naught is the entropy at 0, at 0 Kelvin, and it is the temperature T. So the third law enter into the picture, and it says that for a homogeneous substance, S naught is 0, right? That is referred as third law. So you have an absolute scale, absolute reference for entropy, but there is no such reference for enthalpy, basically, right? It doesn't matter. If you need to know just delta S, so it is not a problem, right? So third law of thermodynamics, it was proposed in 1906 or so by Nast, and it was further modified. So again, like I'm just bypassing this slide and telling you the conclusion. So what is the conclusion is that that the absolute entropy is zero at 0 Kelvin for the homogeneous substances, right? So, like, and that Nast, he said that probably Nast said that it is true for the solids, but Planck offered some correction, and that correction was that it has to be a homogeneous substance. That is the condition. It should not be in solid, liquid, gas, nothing like that. So correction by Planck, who stated that the entropy of any homogeneous substance which is in complete internal equilibrium, two conditions: it should be homogeneous. Second is that it should be complete internal equilibrium. It will be zero at 0 Kelvin. So this is referred as the third law of thermodynamics, which gives the reference of the entropy. Let me go to the next point, right? So again, like, let me bypass this slide, okay, because we have already discussed this point. So let me go to the next point. Now, that we need to refer to certain dimensionless quantities. It is required to make your phase diagrams, basically, phase diagrams, and in order to understand the mixing behavior. So we know that dg is equal to vdp minus sdt plus some additional term, third term. But what if that your temperature remains constant? So dg is equal to vdp minus sdt. So sdt term will go away, and if it is closed system, so the third term will also go away. So dg is equal to vdp. This is correct. Two conditions. Condition one is that it should be closed system, and second is that you are doing the process at isothermally, means keeping temperature constant. So dg is equal to vdp, it will work. And as we understand that working with the solids and liquids, it is not simple, it is tricky. But working with the ideal gas, it is simple. So let us replace this V by RT by P, PV equal to nRT. And if you are working with 1 mole substance, so you can write it RT by P, okay? So, and since this process it is being done, we are considering a process which is being done at isothermally. So RT is constant. So it can be written as RT, and dP by P can be written as d of ln of P also. And now if you are going to do integration at both ends, and that key, and here the temperature remains constant, and we are trying to understand the effect of variation of pressure from P1 to P2. So it is RT of ln of P2 by P1. So the change in Gibbs energy, keeping temperature constant and varying pressure, that is equal to RT ln of P2 by P1. This is true for the ideal gas, okay? But now the question is that the one question may be coming to your mind is that the substances are real, they are not ideal. So why we are using the ideal gas behavior? Because there was no way to understand the material behavior, basically. That is why we started with the ideal gas. Gradually we'll try to develop protocol for the real gas and the liquids and the solids, and this protocol will work. So this equation can be rewritten as, like, if we take P1 as 1 atmospheric pressure, right? So whenever, so that is the reference pressure. So this is a ratio, and we are going to write this ratio as P, but you understand that it is not a pressure, it is a ratio, basically, right? And here, that here at this pressure, we are going to write it as G naught, okay? So this naught, and if you are using naught, means you are at 1 atmospheric pressure first, and second is that you are using pure substance, then it works. So this equation we have derived for pure component, which is gas, ideal gas. So Gibbs energy at any pressure P and temperature T, that is equal to G naught T. And this is G naught, it is the Gibbs energy at temperature T at 1 atmospheric pressure. And this is RT and P. This is the same, this P and P, this P is the same P. But here in the ratio, you have to take 1, basically, right? Let me go to the next. So sometimes it is referred as G equal to G naught plus RT and P. This is one basic fundamental equation, right? And this equation will help us to connect with the real material behavior. We are starting with the ideal behavior, no doubt, but we'll go to the real material behavior. Now the thermodynamic treatment for the non-ideal gas. Now the natural question is that this derivation we have done it for the ideal gas, but we know that it is not going to serve our purpose, right? So again, what if the gas is non-ideal? So dg equal to vdp, the same term we are repeating, and dg equal to rt ln of d ln of p. There is no difference between the previous slide and this slide. It is exactly the same. But there is one difference. What is the difference? We are introducing another ratio, which is small f, and we refer it as fugacity, right? And this fugacity is nothing but the effective pressure for the real gas. And this fugacity concept, it works for the liquids and solids also, right? So this is a big jump we take from the from the ideal gas to the real gas or real material, right? So in place of P, we are defining it F, and we refer it as a fugacity, and it is referred as that effective pressure of the substance. So if you are going to change F, so there will be change in the Gibbs energy, right? Let me go to the next one. Now we are trying to understand the mixture of ideal gases. Okay, so now a question may be coming to your mind, that we want to mix two elements in solid state. We want to mix two elements in liquid state. But why we are referring to mixing of gases? See, very layman's answer to this question is that gases, since they have high entropy, they have good tendency to mix. Crudely speaking, if you take any 2 or 3 gas and put them together, they have tendency to mix. That they don't put a condition that we are not willing to mix, right? But let me take another example. That what if you take water and milk and you put it in a container, whether water and milk will mix? The answer is that from your practical experience, we know that they mix, right? And they form a homogeneous substance. But let me take another example. If you take 1 liter mustard oil and 1 liter water and put them together and put it at room temperature and atmospheric pressure, whether it will mix, you'll find that initially it will mix, but it will segregate. So the question is that why it will segregate? Because these molecules of the water and molecules of the mustard oil, they don't like each other. That is why they segregate. So mixing, you can take it almost granted for the gases, but you cannot take it granted for the liquids. Similarly, whether 2 solids will mix in the solid state, that is the next question. So, that again, the mixing tendency in the solids, it will be there or not, it is another question, right? So that is why initially we are going to develop the protocol, thermodynamic protocol for mixing of ideal gases. Then we'll gradually switch over for the mixing of non-ideal behavior. Okay, so quickly, I will finish it. I know that my time is up. Okay, it is 12:48 or so, and I have to finish it quickly. So this is how we define the mole fractions. Here it is being assumed that we are attempting to mix A, B, and C. These are the 3 gases or 3 components we are trying to mix. So this is how XA, XB, and this is how XC is defined. It is something very simple, right? And this is the partial pressure of A, B, and C. And if you put them together, this is the total pressure of that container, right? So before we go ahead, we need to understand another thermodynamic property, which is called partial molar quantity. So the molar value of any extensive state property of a component of a mixture, it is referred as partial molar value of a property. It is slightly tricky, it is not as simple, though I'm going fast, but it is tricky. We should spend more time to understand it. But if required, you can ask me. Feel free to ask me to clarify if anything is required. This value is not necessarily equal to the value of molar property or the pure component. It may be, it may not be. It can differ also. So the question that why it can differ, if you are going to put A and B together, why this? If you want to find out that what is the molar value of a particular property for a particular substance, it can differ. Why? Because when A is separate and B is separate, that is one thing. But if you are going to mix them together, there will be molecular interaction, atomic interaction, molecular interaction between A and B. So that they are going to influence each other. That is why these partial molar quantities, when you are going to mix them together, they can change. So this is one important point which we need to understand in our further discussion. So the partial molar quantity of any extensive property Q of the component I in a mixture of component IJK, it is referred as QI bar. Okay, and it is defined as dou Q prime divided by dou Ni, keeping pressure, temperature constant, and other thing constant. This is how we define the partial molar quantity. So example, that G is an extensive property. So in place of Q, if you are going to put the G will appear like this. Okay, and it is a coincidence that G of the ith component, when it is in solution form, bar always refers that you are in solution form. Solution in the sense that you are in mixture of solution form. And it coincidentally, it is as good as chemical potential of that substance in that solution. Let me go to the next slide, right? So the partial molar quantities, the ideal gas A in a mixture of ideal gas. So D of GA bar, it comes out to VA bar DP, right or not? So DG is equal to VDP. We are familiar, but it is not simply putting bar. Before we put a bar, we need to mathematically prove that this equation is true. But in order to save some time, I have bypassed it, right? And it is being said that it is possible to prove that VA bar that is equal to XA mole fraction of A RT by PA, something like that. And again, DG bar that is equal to VA bar DP, and you have to replace this term over here, and DP can be written in this term basically, right? So I'm not entering into the finer details, rather than I'm helping you to form a notion that what is the materials thermodynamics and what is the phase diagram and how it is useful for materials purpose, materials application. So that is why I'm not entering into finer details. Now that this or RT is going to come over here, so it comes out to be D of ln of P. So if you spend 5-10 minutes, it is possible to do this derivation on it. Now what we are doing is that we are doing integration both sides. So if you do integration, the proper limits, and it is RT of ln of PA also. Now PA can be written as this is the partial pressure of A. See, please remember that we are still considering the mixing of ideal gases. Okay, so PA can be written as XA, which is mole fraction of A, and this is the total pressure. This is how we can write it. Let me go to the next slide. Now, that we have to be always careful that what is the heat of mixing of ideal gas. So what is the meaning at all? What is the notion of heat of mixing? So if you have three gases which are separate, they must have some enthalpy. If yes or no, and if you put them together, all the gases, if you put them together, right? So what will be the new heat of mixing? So if you take the difference, the heat of mixing after mixing and before mixing, and if you take it, so that is referred as heat of mixing. Okay. Similarly, there is entropy of mixing, right? And if you know heat of mixing and if you know heat of entropy of mixing, so you can find out what is the Gibbs energy of mixing. So if Gibbs energy of mixing, it comes out to be negative, means mixing will take place, and if it is positive, it will never take place. As simple as that. So this is why we have to do so much thermodynamic protocol, and it is not only for the gases. This protocol can be applied for the liquids and the solids, and that is the power of this thermodynamic analysis of this right. So so for example, for each component gas in a mixture, Gi for the ith component, and it is bar means it is referring to the molar Gibbs energy of the ith substance. That is equal to Gi naught. Gi naught means when the pressure was 1 atmospheric pressure and when it was pure. So this was the Gibbs energy plus RT ln xi plus RT ln p. We have seen the derivation. Now the point is that let us divide every side by T, and if if the left hand side and right hand side by T, and if you differentiate it with respect to T, so it is possible that this left hand side is equal to right hand side. Why? Because this is the T and R is constant, ln xi is constant. Again, R and ln p is constant. So these two terms become constant. So if you differentiate with respect to T, this term is going to go away. So these two terms we are going to be left with, right? So what we want to prove actually, so that there is one equation which connects G by T with with H. So that this is the left hand side and this is the right hand side. So it proves that Hi bar that is equal to Hi naught. So what is the physical significance here? It says that enthalpy of the pure component and enthalpy of the ith component which is mixed is same. Means there is no change in enthalpy, and that is a condition of ideal mixing. That is there is something referred as ideal mixing. So change in enthalpy due to mixing is zero. There is no change. Means that just due to mixing there is no change in enthalpy, right? And this is referred as ideal mixing. Please, but mind it that entropy is going to change. Entropy will not remain same. We need to understand this. Okay, so Gibbs free energy of mixing of the ideal gas. So for each component of gas I in the mixture of ideal gas, so Gi bar that is equal to Gi naught plus RT ln of Pi. This derivation we have done. Okay, and so for each component gas before mixing, so Gi, because we are not putting bar, so Gi when it was pure, Gi naught plus RT of ln of Pi bar, it's pressure basically, right? And it has to be kept in atmospheric pressure. That is, then that if you're going to change the pressure, so how the Gibbs energy for the pure component it is going to change, we know. Now that you are doing mixing. Mixing means initially you have three gases which were pure. Now you put them together. So there is change in state from unmixed to the mixed state. So what we are doing, that change in Gibbs energy. This is the total Gibbs energy of the mixture minus this is the Gibbs energy of the unmixed compound. So if you take the difference, this is, and if you do a little bit of mathematics over here, so you are going to get that change in delta G. It comes out to be like this. Okay, so and Pi by P, capital Pi, it can be referred as Xi. So this is the change in Gibbs energy, right? And this is a negative term. Why? Because Xi is always less than 1, basically. So this is a negative term. So it says that for the gases, they have tendency to mix because the delta G comes out to be negative. Let me go to the next slide. So can we find out what is the change in the entropy of mixing of the ideal gas? So we know that delta G prime mix, that is equal to delta H prime mix minus T delta S prime mix, and delta H prime mix is 0. We have proven it. So if you have expression for delta G, you can find out what is the expression for delta S. So that this is the expression for delta G and this is the expression for delta X. But this is a positive number. Why? This is a negative sign, but ln of xi, this is negative, 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 positive. So if you are going to put three gases together, its entropy is going to increase. This is the point basically. I guess that we understand up in here. Now the question is that till now, whatever the thermodynamics we have seen, it is for ideal mixing. What about non-ideal mixing? We'll try to understand that. So the thermodynamic treatment for the non-ideal gases, right? So again, dg is equal to vdp, and this expression we are familiar, right? Now the function is invented, which is used, what is that function that is referred as fugacity? In dg is equal to rt d, and in place of p, if you put, it is fugacity, and fugacity is nothing but the effective pressure of any component, any substance. Okay, so and so if you do integration, g comes out to be g naught plus rt of ln of f also. Okay, now we need to understand there is something called thermodynamic. It is 12:57. May I have another 5 minutes to finish? May I have another 5 minutes, please?
Okay, sir.
Okay, so the thermodynamic activity of component in solution. Here, that you have put at least two components or three components together. So what is the notion of thermodynamic activity? Thermodynamic activity, it is defined for the ith component, that is equal to Fi. That is the fugacity which we have discussed of the ith component divided by Fi naught. So what is this Fi naught? That this is the fugacity, is the effective pressure when it was pure, and this is the effective pressure when you put it in the solution. Now this fugacity, it refers, that physical meaning of this fugacity is that it captures the interaction with the surrounding. And here, this fugacity is the effective pressure when it was pure. So this ratio is referred as activity. So mind it that activity is always, activity is always a ratio. It does not have a unit. First point. Second point is that if you take a pure substance, so Fi will be exactly equal to Fi naught. So activity of a pure substance, it will always be equal to 1. We need to know this much. Okay. Now, what is this heading? I'm unable to read it. But the change in the Gibbs free energy of the component I due to formation of solution. This is the most critical aspect. That what if, how much Gibbs energy is going to change if it is going to move from pure state to solution state, right, in the mixed state. So pure component I occurring in a condensed state at temperature T exerts an equilibrium vapor pressure of Pi naught. Okay, every liquid or every solid, every condensed phase, it is going to exert some equilibrium vapor pressure. And when occurring in condensed solution at temperature T, right, and it exerts a lower equilibrium pressure Pi when it is in solution state. When it is in pure state, it is going to exert more, and when it is in, like in mixed solution state, so due to atomic interactions, this exerted pressure will be less, and we are referring it as Pi. Consider the following isothermal three-step process. Actually, what we are interested, we are interested to find out what is changing the Gibbs energy. So we are dividing the entire process in 3 steps, and if you sum up these 3 steps, that will lead to the entire process of a pure component entering the solution, right? So the evaporation of 1 mole of pure condensed I, okay, condensed in the sense it can be solid or it can be liquid, to the vapor I, and it is creating pressure of Pi naught. Okay, so this is the process 1. Process 2 is that decrease in pressure of 1 mole vapor from Pi naught to Pi. Okay, initial pressure was this, and somehow you have decreased the pressure. And third is now the condensation of 1 mole of vapor I from the pressure Pi to the condensed solution. So that ultimately, if you critically analyze that what effectively we have done in step A, B, C, so you will come to know that we have put this pure component in the solution. So that is the sum total of ABC, right? So the change in Gibbs free energy of component I due to formation of solution. So what we are doing is that delta GA plus delta GB plus delta GC. Now it is noted that delta GA, since this process A was in equilibrium process, so delta G will be 0. Delta GC will also be 0 because that was the equilibrium process. And in equilibrium, delta G is always 0. So its total sum comes out to be delta GB, because there is change in pressure, and we know that what will change in Gibbs energy due to change in pressure, R, because it is equal to RT and ln of Pi by Pi naught. This is change in pressure, so this is the change in the Gibbs energy. So basically we have found out that if a pure substance, it is going to enter in the solution, whether there will be change in Gibbs energy, yes, there will be change in Gibbs energy, and how much change. So this is the change basically, right? So Pi by P naught, or you can write it like Fi by F naught, and this is nothing but this is equal to activity. So change in Gibbs energy once a pure substance is entering into the solution, that is equal to RT ln of activity of A. This is the point I want to put across, right? So this we have written that it is RT ln of A of I. Okay, so this is a change in the Gibbs energy, right? So, and now we are going to refer is that a change in Gibbs energy of the ith component when it is in mixture state, and this bar stands for the solution. So GI bar. So this is the molar Gibbs energy of the ith component when it is solution minus molar Gibbs energy the ith component when it was pure. Take the difference, that is equal to RT of ln of A of I. Right, this is the activity of I when it is in solution. So this is very important step for us to move ahead, right? So actually, I will very quickly we will connect all these derivations with our phase diagram. Okay, and this phase diagram will tell you that how the phases form. Okay, and initially we'll see about the binary system, then we'll go for the ternary system like that. So changing Gibbs free energy due to formation of binary solution, right? So see, this is the Gibbs free energy before mixing. So this was the molar Gibbs energy of the component A, and this is the molar Gibbs energy of component B. And since the Gibbs energy it is extensive property, so number of moles has to be multiplied. So this was the total Gibbs of energy when these two components they were kept separate in two different containers. But if you put them together, so what is happening is that now this is the molar Gibbs energy of component A. Okay, when it is in mixed state, this is molar Gibbs energy of B, which is in big mixed state. And initially for the beginners, they think that GB this let me say that this is GA bar and GA naught, it should be same, but no, since due to interaction Gibbs energy is going to change. So GA naught is not equal to GA bar, it can change basically. So this is the Gibbs energy after mixing. So what is the difference? You take the difference. So you have to take the difference. And so in the next slide what we'll do is that we'll take the difference. So here this is, if you look at the first term, this is the Gibbs energy after mixing, this is the Gibbs energy before mixing, and you take the difference. This is the difference, and this we have already calculated basically, right? So
Sorry to interrupt.
now, yeah.
Late for next session. We are 30 minutes late.
Oh, so should I stop now? Should I stop?
Conclude.
Oh yeah, I should stop. Oh, okay, I should conclude. Okay, so in order to conclude, I have to move very fast now. Let me see how I can conclude. Let me see. Okay, so in this slide, it is heat of formation of ideal solution. It is there is no change in heat of formation, but there is change in that there is change in entropy in formation of ideal solution, right? And this is how that if you are going to put A and B together, so the entropy it is going to it is going to change, and changing entropy it is positive, right? And again now what we are going to do is that we are going to see that how this protocols it works for non-ideal solution, right? So here it is that if you are going to put iron and nickel together, and let us see how it is going to mix basically. So we find that activity now for the this is straight line behavior, this is ideal mixing, but there is a departure, and we refer that it is a negative departure. It means that the atoms of iron and nickel they attract each other. That is why there is a deviation, negative deviation. Okay, so that is why there is something called activity coefficient gamma I. It is less than 1. So we are considering iron and nickel at 1600 degrees Celsius, right? So this is referred as negative departure. But if you talk about iron and copper at 1550 Celsius, there is a positive departure, and meaning of positive departure that iron and copper they don't like each other. That is why that the activity has increased. And if we go to the next slides, so for the non-ideal solutions, again what we have to do is that we have to understand that what is the change in enthalpy and what is the change in entropy and what is change in Gibbs energy, right? So here it is a mixing of the tin and the thallium it is being considered. So the enthalpy it is positive enthalpy coming. Here it is a composition. So enthalpy is positive, and this is entropy change into negative. And this how the change in Gibbs energy it is for a petrol system at 14 Celsius we can find out. Now how the free energy per mole of the mixing is going to change. So initially it is a linear change. That there is linear behavior. Now free energy of the mixing of the ideal solution. So at low temperature, the delta G mix, it looks like this, and at high temperature, it looks like this, right? Now, what we are going to do is, but this is the linear behavior, and after mixing, the molar Gibbs energy it is going to change like this, right? Now, this is something very important and interesting. Here, that we cannot or assume that your delta G mix for liquids and solids, it will always be negative. This is a condition under a particular composition region, this delta G becoming positive. And if the delta G is positive, so at this temperature and in this composition region, these two materials, they are not going to mix. Okay, so this is something important which I wanted to convey. Now the point is that if you take A and B, okay, A is one element and B is another element. So how it gives energy, it is going to change with respect to mixing. So this is how it is going to change. Now you know that if this is, if we say that this is one phase, alpha phase, and it is and its gives energy is appearing like this. So if you are, what is alpha? Alpha is nothing but in A you are going to put a slight amount of B, and as you continue to put the B, so here the Gibbs energy is increasing. But if you continue to further increase B, so its Gibbs energy it is going to increase like this. So this is one curve. Similarly, if you take pure B and you continue to put some amount of A into it, so initially its Gibbs energy is decreasing, then it is going up. So this kind of two curves we are having basically, right? So there is something interesting happening, you know, that you can put a tangent over here. So you know, in this region, alpha is purely stable, and in this composition region and at this temperature, beta is stable. But here, a mixture of alpha and beta, it is stable. So it becomes a two-phase region basically, right? And this, so here, you know, like you look here at that this is called isomorphous phase diagram. Okay, for copper nickel it is true. So if you are at higher temperature, it will be in liquid and it is going to mix. At lower temperature, you are somewhere here at this temperature composition, there will be liquid and solid. And if you are going down, so there will be one solid solution. And this is how the Gibbs energy, it is going to Gibbs energy of the solid and liquid, it is going to change with respect to temperature basically. So using this Gibbs energy diagram, you can make this phase diagram. Okay, let me take another example that, you know, that for every A and B, this kind of phase diagram will come, it is not so. I'm taking another example of A and B, where A and B, they are slightly dissimilar. So this is how the Gibbs energy curve for the solid and liquid it is going to change. And you know that if you have this phase diagrams, you can Gibbs energy composition diagram, using this you will be able to make this phase diagrams basically, you know. So this is liquid, and A and B, they are miscible into each other. Here it is a solid solution, one type of solid solution, this is another type of solid solution, and it is a mixed region of A and B. So this phase diagram, it comes from Gibbs energy composition diagram basically. Is it fine? This is another similar plot. And you know, like here I'm giving you example that if in place of A and B, if you take the third component C, so this kind of complex phase diagram it is going to form. So multi-component is nothing but more than 2, 3, 4, 5. So a real alloys, they are multi-component alloys. So if you understand the thermodynamic behavior of the binary system, you can understand it for the more components, right? Now the alloy characterization which we do using optical microscopy, scanning electron microscopy, transmission electron microscopy, and XRD. So in optical microscopy, we use magnified image, we use normally compound microscope, and visible light is used, and normal magnification it is in range of 10 to 1500 magnification. Now the question comes that why we can't go for higher magnification. You have to continue to put the magnifying glasses together, and you can go for the higher magnification. You can go for 15,000 also. But no, it is limited by resolution, and the formula of resolution is 0.61 lambda by Na. Na is nothing but numerical aperture. So here we use the visible light, and it is in range of 3,800 angstrom to 7,800 angstrom. So the resolution remains limited. So increasing magnification doesn't help, right? And there is important experimental aspect of sample preparation. You have to do sample mounting, grinding, polishing by emery paper or cloth paper, and etching. And after that, you watch your sample under optical microscope. And sometimes we go for electropolishing also. So, you know, like you can't go at very high magnification. So what we do is that we go for a scanning electron microscope. So we used electrons in place of light, and it is a surface-based technique, and it is used for imaging purpose, and it is used for, you know, to find out the elements present and their composition. And but the limitation, it is a surface technique. The third technique which is used for metal characterization, which is electron microscope. So electrons are used, it transmits through the material, very thin samples is required or prepared, and sample is polished by emery paper till, let us say, 300 microns or so. And after that, you need to go for electropolishing or iron grinding. You have to go for till perforation takes place. And in that close to the perforated region, you put the electrons, and you know that you can use it in the TEM, you can use it in image mode and diffraction mode. And you know, in order to do phase analysis, that which particular phase is formed, we go for XRD. So you use primarily for phase identification, various other applications like quantification of phases and stress analysis, and it is based on the Brecht's law, right? And so this is how we synthesize alloy, and this is how we do the primary characterization of this metallic materials. Okay, so this is my last slide, and I'm sorry I have taken more time. It is done at my end. If you have any question, you can ask me.
Sir, our session is getting delayed, so we don't have time for interaction. So thank you very much, sir, Dr. Manu Pati, sir, for your excellent lecture on synthesis and characterization of multi-component alloys. This talk, sir, this talk will surely be helpful in igniting the interest of new researchers and participants. Thank you very much, sir.
Hello.
Hello.
It's about the next talk.
Yes, sir.
Start.
It is my pleasure and honor to introduce Professor Anjali Awadhya ma'am, Professor of Physics in Government Nagarjuna PG College of Science, Raipur, Chhattisgarh. She has academic and research experience of 33 years. Her thrust area of research is electro-optical studies of nanomaterials and published more than 57 research papers and book on nanoscience. So I would like to invite Professor Anjali Awadhya ma'am. Please, ma'am.
Hello. So please share my PPT. Very good afternoon to all of you. I took this opportunity to discuss something which I always wanted to discuss with my students, because they have been working in the field of SISTA for last 5 to 6 years now. So we must understand, as a physicist, I always wanted to communicate that SISTA is just a tool. It's not everything. It is a tool for us. For physicists, it is a tool. So whenever we are learning a new tool, we must understand the physics behind. So if we are leaving physics behind and learning something, just some commands and everything, so you will not be able to use that tool efficiently also. Because you don't know the initial conditions, what's going on, why we are changing, why we are giving such and such inputs, why they require such kind of inputs. So we must be particular about the system on which we are working, and we must know the physics behind the system. So that's why I took this opportunity to communicate, because most of the participants belong and have a physics background or chemistry background maybe. So because it is a multidisciplinary subject. So we have to think about the material first, about the system first, and then use this tool to describe various properties of that material. So here's my presentation on electronic and optical properties. We calculate using SISTA. So next slide, please. So as you know, SISTA is a Spanish initiative for electronic simulations with thousands of atoms. Next, please. It is a method and its computer program implementation to perform electronic structure calculations. First thing, and second is ab initio molecular dynamics simulations of molecules and solids, which was described very beautifully by Preetham Panda sir in the morning session. Main characteristics of SISTA is that it calculates the Kohn-Sham self-consistent density functional method it uses. And it uses local density and generalized gradient approximations. As a student of quantum mechanics, you are well aware that we don't have exact solutions of Schrodinger equation. We need a lot of approximations to solve the Schrodinger equation for any such system. So here we are having, because we deal with a small number of molecules, a small group of molecules. So we are actually dealing with nanomaterials. So in nanomaterials, we need to, if we want to solve.
Sorry to interrupt you, ma'am. Your slide is not in presentation mode as well as not changing. We are in the just first slide, the title page.
Okay. So, please coordinate. It's not in presentation mode, there's. You are host now, Rashmi. Yes. पहले presentation share the slide में जाइए.
Ma'am, you can simply press. Okay.
Okay. Your screen sharing, yes. So now is it visible, sir?
Yes.
Okay. Sorry. So we now it's okay. Now it's okay. Usko off. So we calculate Kohn-Sham self-consistent density functional equations in local density approximation and GGA. They have been talking, we have been learning about these, so we won't go into the details. And we can also include van der Waals interactions, and it uses norm-conserving pseudo-potential method. This is very important, which we will discuss in some detail. Next, please. So can you remove that that window above? Yeah. Just drag it somewhere else. So it uses atomic orbitals as basis sets. So basis sets are very important. Basis sets are actually, we can use the basis set along with multiple zeta functions and angular momenta polarization and off-site orbitals. We can construct the orbitals using these basis sets. So the what does it describe? It describes the radial shape of every orbital numerically, and any shape can be used. So we can have various molecules of various shapes, and we can design we can use SISTA for them. We can design our basis sets depending on the kind of system we are using, the kind of molecules we are dealing with. Second, next slide, please. Yes. So it projects the electron wave functions and density onto a real space grid. ये SISTA के बारे में, this we are talking about the SISTA. It projects the electron wave functions and density onto a real space grid, K grids you form, and it allows the use of localized linear combination of occupied orbitals. In the valence band, we have all occupied states. So they are depicted as a linear combination. It is written in Fortran 2003 as far as I got the information, and it may be compiled for serial or parallel execution. So this was all about SISTA. So next slide. It it calculates a lot of things. You all have been exposed to these kind of information, so I will just skip it. So please go to the next slide. So these are some, it also includes the ballistic electron transport, which we are studying in for nanomaterials. So this can be done through transistor also, and along with the band structure, electronic structure, optical, magnetic and mechanical properties. Next please. So what is DFT? The density functional theory maps a description for interacting electrons onto one of non-interacting electrons in an effective potential. So this describes the DFT basically. If we have multiple or interacting electron system, it is very difficult to solve the Schrodinger equation for that. So we need to modify it and transform it into non-interacting system. For this we use the pseudopotential method. Next please. The main goal of electronic structure methods is to solve the Schrodinger equation for the electrons in a molecule or solid, to evaluate the resulting total energies, forces, response functions and other quantities. Input requires, now this is the beauty of the first principle studies, we need very few information. That's the basic system we need to know. What do you give in the input? You just give the information about the charge and mass of the nuclei, number of electron and initial atomic geometry. That's all you need, and you can calculate everything you want to calculate, which system offers. Next please. And then the experimentalists always bother about the accuracy of the theoretical simulation work. So here is the accuracy part, which Pandey sir also discussed in his lecture, that they predict the following parameters. Binding energy is accurate within a few tenths of an electron volt. That is fabulous. Then bond lengths in the 1 to 2% range, the dynamics of atoms up to tenths of picoseconds frequency. And then systems with few hundred atoms per unit cell can be handled, and quantities related to energetics, atomic structure and to the ground state electronic structure can be extracted. So this is a wonderful software developed by SISTA, and we are very grateful to the SISTA developers for providing it free to all over the world, and researchers and PG students and those who are interested in modeling. Next please. So what is Kohn-Sham equation? It is simply one electron Schrodinger equation. We can say it is simply a one electron Schrodinger equation in which the effective potential is replaced by potential method. It's a one electron. As equation can be derived. So I'm not going into the detail because I will focus on the properties which we have to calculate using these equations. Now there is a problem. What is the problem? What kind of basis set we should use? So you must know that the lattice contains atoms arranged at particular lattice points, and there is a space between two atoms. So when the electron comes near the nuclei, there is a lot of turbulence and wavy structure, wave patterns are there. So wave function and the basis set should be small to address those oscillations in the wave function. And secondly, when we go to the bonding region, that is between two atoms, then it is a steady one, exponentially decaying wave function is there. So in the bonding region between the atoms, the kinetic energy is small and the wave function is smooth, then there we should use large basis sets. So there is a contradiction. Near the nucleus, we should use a small basis set, and in between the atoms, we need to use the large basis set. So we have to compensate, choose the basis set most accurately. So this is the physics part. Why should we choose this particular kind of basis sets? There are several. There are simple basis sets, plain just one zeta potential basis sets are there, minimal basis sets are there, and then there are double zeta and various kinds of basis sets are there. So now what to choose? It depends on the problem you have taken. What do you want to study? Whether you want to study the nature, the interaction between electron and the nucleus, or whether you want to study what is happening in the empty space within the crystal. So next please. So this is done through pseudopotential method. Okay. So what is this Let us discuss briefly. Next, please. So assumptions, what are the assumptions? How do you form pseudo potential and what are the assumptions? So in order to construct a first principle pseudo potential, one starts out with an all electron density functional calculations. They yield the atomic potential and wave functions. Due to spherical symmetry, the radial part of the wave function for different magnetic quantum numbers m equal to 1, 2, 3, 4, okay? They are identical. So there is a radial symmetry. So various orbitals have similar kind of wave function. They can be represented by similar kind of wave functions. Next, please. So how the basis sets are formed? The basis set in theoretical and computational chemistry is a set of functions called the basis function that is used to represent the electronic wave function in the Hartree-Fock method or DFT method. You know that the wave function is replaced by the density function in this SISTA calculation. So that is presented by the basis function. So density function is presented by the basis function, we can say. In order to turn the partial differential equation of the model into algebraic equation suitable for efficient implementation on a computer. Now you know this is a computer program. So it is very difficult to solve differential equation. It will cost of simulation and modeling will be more if we use complicated operations. So we have to change all the computation to simple algebraic calculations. So for this we are using this bracket notation, because you are being taught quantum mechanics also. So you have been using these bracket notations where we use simple matrix algebra to solve the equations. So similar thing is here being employed by the SISTA developers. So we need a basis sets. The single particle states or the molecular orbits are represented by those basis sets. So here is a catch again, that the single particle state should be are chosen as molecular orbital basis sets. There may be Gaussian type orbitals, Slater types orbitals, or numerical atomic orbitals. Various shapes can be chosen as per your requirement. Gaussian is the symmetrical one, Slater is a peaked one, so various kinds of basis functions can be chosen as per the requirement. Next, please. The smallest basis sets, that's what I was discussing. The smallest basis sets are minimal basis. And they are quick to run. So the calculations will be done very promptly and you will need no time. So when you use basic minimal basis, then there is computation time is saved, but the information is lost. Okay, so we don't want the information to be lost. We want more and more information about our system, and that is why we add zeta functions. Now what are these zeta functions? Next, please. Actually, these zeta functions are just the orbitals. If we are having a hydrogen atom, it is having a simple s orbital electron. But if hydrogen is making bonds with other species, other chemical species, then we need to add p orbitals at least. Okay, so as you can see here, a p orbital, double shaped p orbital is there, and then the d orbital is there. And when they overlap, so if we use double zeta function, you say, in the basis set you are using double zeta, then it will make a polarized orbital. So it's having a specific direction. Because the chemical bonds are always polarized, they are directional. You must be knowing that in H2O, they are having 102 degrees angle between O and H and 2H and 1O atoms, molecules. So this is what we need to know about choice of our basis sets. Next, please. And it is very important that the basis set converges. So for that, what we can do is we can add more zeta functions, and we can add more exponents for getting better results. And we must know one thing is there, that 1 Rydberg is equal to 13.6 electron volt, and you always use this unit for measurement. And lambda is equal to 2 pi g is called the plane wave cutoff. So we have to be very particular about the cutoff of the system. So we have different K points, and 2 pi by G is the inverse, that is constant for that, related to each K. And so we have to be aware about the cutoff point of the system. Okay, next please. Now we come directly to the calculation of electronic properties. So in electronic properties, what you calculate is density of states basically. So what is the density of states? It is dN by dE. You must be remembering, it is taught in the BSc classes also. Number of energy levels per unit energy value, per unit electron volt, you can so say. Okay, so there are several options to obtain the total density of state. So you know, we have to simulate the physical thing into a program, a computer program. And how are we going to do it? We have to do it through some calculation. We have to calculate some formula, and then we will get the result. So how do you get the peaks you are getting in the DOS and PDOS and the exact band gap which is there for that system? So first thing to calculate, how to calculate DOS, is the Hamiltonian eigenvalues of SCF, sampling K points, can be dumped into a given format, and it will calculate the density of states. So these commands you must have practiced by now in the last 2 sessions, hands-on sessions, how to calculate DOS. So this is what the SISTA developers have done, that you have to, as input you give for various K points, you give the Hamiltonian eigenvalues. You assign Hamiltonian eigenvalues to each K value, and this is how at each K value, the Hamiltonian eigenvalues are energy eigenvalues actually. So how many energy eigenvalues means how many energy states are there for each point. For at each K, you are getting density of the states, that is number of energy levels attached to each K point. So this is how the programming is done. In all cases, the units for DOS are number of states per electron volt, and the total DOS is normalized as summation of GeDE equal to number of basis orbitals in unit cell. So you calculate total number of orbitals in a unit cell. Next please. And PDOS is, SISTA will compute a full decomposition of DOS over all orbitals. What is the contribution of s orbital? What is the contribution of p orbital? What is the contribution of d orbital? What type of contribution? How many energy levels are attached to s orbital? How many energy states are attached to p and then d orbitals? So individual contributions also can be calculated using SISTA, that is PDOS. Okay. Next, please. There was one point I missed. It can be done also through COOP calculations, which is a bit advanced. Learners of SISTA know, but it will not be covered, I think, in this session. But you can always go to the tutorials uploaded by Verma sir and others in the SISTA experts and learn from there also. Okay. So we have come to now the optical property calculation. So what do we calculate actually? We must know both the physical system and the computer program which is developed to simulate that physical system. Okay. So what is the physical system? Whenever light falls, how do you study optical property? Light falls on some material and there is some kind of interaction. Light may be absorbed, light may be transmitted. Okay? Light may polarize the material. It can generate dipole moments, electric dipole moments in the material. That is how you know about that there is some change in the state of the system, and that is calculated through SISTA. Okay, so it calculates basically the polarization due to falling of light on a material. Okay, light is an electromagnetic radiation, you know. So when you apply in SISTA initially, if you want to polarize a system, you have to set the energy value to particular value. Okay, you have to apply the electric field. You have to apply the electric field, then polarization will take place, and then everything will follow. Okay, next please. So the optical properties, basically SISTA calculates the imaginary and real part of the dielectric function. This is the dielectric. What does it calculate? Dielectric function. What is the physics behind? Actually, it calculates the response of a material to optical stimulations. Okay, whenever optical stimulations, any range. It may be IR, it may be UV light, it may be visible light. What is the response of our material to that light? That response is the property of the material itself, and that is called as dielectric response. So if we know the dielectric response, we can calculate reflectivity, mu, and optical absorption, reflectance, everything in terms of that epsilon. Okay? So we calculate epsilon, both the imaginary and real part of the dielectric function using system. So next slide please. There is a simple formula which will tell you, yeah. So first and the basic thing which SISTA calculates is the atomic polarizability. Okay, so atomic polarizability is number of electric dipole moments created by applying electric field, and it is proportional to the electric field. So P is equal to alpha, that is the atomic polarizability of the material, times the field applied, and they are frequency dependent. So this is the basic physics which you have been studying from your school days. Okay, so this is how polarization or atomic polarizability is defined. There are complicated formula, and here the alpha is calculated first using this formula. Okay, so first thing is we calculate alpha, and in terms of alpha, please go to the next slide. In terms of alpha, this imaginary part of epsilon is calculated. So this is the simple correlation between the physical situation and simulation. What simulation is calculated and calculating and how. So as a physics student, you must have a question: how this SISTA can calculate a physical event? How can it simulate a physical event? Okay, light is falling on something. So how can it calculate the dipole moments? How can it calculate the reflective index, refractive index, and everything? So here is the clue, that it calculates the polarizability. Polarizability is directly related to the epsilon, that is the dielectric constant, real and imaginary parts. Next please. Commands I am leaving because maybe Narendra will address these commands in the last session. So commands I am leaving. Okay. Then this electric, if you remember, there was a Krennig transformation model. That it will come afterwards. So if we are using a metallic surface and light is falling on it, then the theory is slightly different. So a new term will appear for metals, and this term has to be added when we are giving the inputs. So if our material is a metal, then we must add this Drude term for the metals. Okay, next please. These settings, there is a very important setting which our student missed actually. So when I came to see this operation in the SISTA manual, then it was quite interesting, because the tendency of DFT calculation to underestimate the band gap. Band gap is underestimated. We need this scissor operation so that we can change and match the band gap to the real value of the band gap. So this must be done. Whenever you are doing the band gap calculation, always use this scissor operation, but this is done in the optical settings only. Okay. Now there is restriction on the number of orbitals also. Okay. How many number of bands should be there and should be included to calculate the optical properties? Sorry. So there is a restriction. The number must be larger than the number of occupied bonds. The number of bonds or number of occupied energy levels in the valence band. Okay, and less than number of basis functions. Okay, next please. Now, yesterday Narendra did something. There was a spiked DOS graph. Then he introduced some kind of broadening, and then those peaks turned into Gaussian kind of peaks. So the peaks of the DOS and PDOS can be adjusted. Okay, using this K sampling and broadening tool. Okay, next please. Next please. So these are some tools which you use for polarization. You can use three situations. One is the system is polarized. That is, it implies that we have applied electric field in a given direction. So the system is polarized. The system may be unpolarized. Light can travel in any direction. And for a polycrystal, we take the average value of electric field and everything. So next please. So these are the files created out of the optical calculations, in which we calculate the real and imaginary part of the epsilon, refractive index, absorption coefficient, optical activity, optical conductivity, lot of things are calculated. Next please. This is the formula. Physicists always want a formula. So this is the formula based on which this Cramer's chronic transformation, which are the basis of the all optical calculations which are done in system. Okay, so you can see there is real and imaginary part. This is called Cramer's chronic relation, and on the basis of this, and in terms of the atomic polarizability alpha, you can calculate the refractive index, optical absorption. Next please. Refractive index, extinction coefficient, reflectance and absorption coefficient, all in terms of epsilon. That is why there are various formula, but I have chosen this formula because everything is written in terms of epsilon 1 and epsilon 2. That is the dielectric response, because the fundamental thing which SISTA calculates is epsilon, and everything else is just a calculation of formula and through formula. So the fundamental thing in calculating the optical properties is epsilon, that is the dielectric response of the material. Okay. So there are non-isotropic material, for we average out everything. Okay, non-isotropic, in different directions we are having different values. Okay, next please. Then there are macroscopic polarizations. This is for insulators. I'm just covering it very fast. Few slides are left, 1 or 2 slides. So macroscopic polarization means if a material is insulator, then your program, your SISTA command asks you to create a band gap, because insulators always have a band gap. Okay, and then across that band gap, the vertical transitions take place in the K band. Okay, next please. If the system is already polarized, you know there are 2 types of materials, polar and non-polar. So polar materials always have these kind of dielectric, these kind of dipole moments, plus and minus ends do not match, they are not concentric. So for these we have to create, because already electric field is there inside the crystal. So we have to create a background electric field. Now you are doing it through a computer program. So you must be aware that if my material is polar, then I must create this background electric field. Okay, but it is not that simple, because you know, as the instruction is given in the manual, that this is easily done in cubic systems, simple cubic, FCC or BCC. For slabs and all, it is very difficult to create a background electric field. So don't even try it. They have given warning for that. Okay, next please. Now, if you want to dope a material and then calculate its optical property, so there are suggestions how can you do it. Okay, so this option instructs the program to add a background charge density to simulate doping. Okay, so these are the things which a physicist must know before using SISTA. Okay, then only you can use SISTA very efficiently. You may be a physics background or a chemistry background, but if you want it a tool, use it a tool. And for a tool, we need a skill training, and that is why this kind of workshop is very important, because you are getting actual real hands-on experience for that. So this was my point which I wanted to communicate. And with this, I come to the end of my presentation. Thank you. Thank you so much.
I would like to thank you, ma'am, for her talk on electronic and optical properties of system. Thank you, ma'am. Now it's time for lunch break. So participants are requested to rejoin at 2:30 p.m. ML Verma sir, are you there?
Yes, yes.
It will be okay to have a hands-on session at 30 p.m.
Yeah, 2:30 today.
Okay. Then participants are requested to join for hands-on session at 2:30 p.m.